Now we're going to review different sets of real numbers. Real numbers, identified by capital R, are numbers that would appear on the number line. And all real numbers are either rational numbers or irrational numbers. But before we define these two sets of numbers, I'd like to start with the natural numbers or counting numbers. Then we'll work our way up. So natural numbers or counting numbers, identified by capital N, are the numbers 1, 2, 3, 4, 5, 6, and so on. So looking at our Venn diagram here, the natural numbers would be these numbers in this set here, again identified by capital N. Next, the whole numbers include all of the natural numbers and the number 0. So looking at the Venn diagram again, capital W represents whole numbers, which include 0 as well as all of the natural numbers. The integers, identified by capital Z, are the numbers that belong to this set here. Notice how it includes the negative natural numbers, 0, and the natural numbers. So again, looking at our Venn diagram, here's Z. Here are the negative natural numbers, 0, and the natural numbers. All of these are included in the set of integers, which now brings us to the set of rational and irrational numbers. So we can see right away that integers, whole numbers, and natural numbers are within the set Q, which are rational numbers. Rational numbers can be written in the form of a divided by b, with a and b as integers. Of course, b can't equal 0. So we haven't included fractions yet, but fractions like 2/3 and -2/5 would also be rational numbers, even though they don't belong to the set of integers, whole numbers, or natural numbers. In decimal form, rational numbers would either terminate or repeat. So for example, 0.4 terminates and therefore is rational, and 0.3 repeats because the 3 repeats and therefore is also rational. So a lot of times when trying to determine if a number is rational, it can be helpful to convert it to a decimal. And then irrational numbers are numbers that in decimal form do not terminate and do not repeat. So for example, square root 5 would be some non-terminating, non-repeating decimal, and of course, so is pi. So let's take a look at a few examples. We want to determine which set or sets of real numbers each number would belong to. So number 1, we have 0. So let's go back and take a look at our Venn diagram. Notice that 0 is here, which means it's a whole number. Then we can work our way out. Z represents the set of integers, so 0 is an integer. Q represents the rational numbers, so 0 is also rational. Then of course all the numbers are going to be real numbers. So again, it's going to be a whole number, so W. It's going to be an integer, which is Z. It's going to be rational, which is Q, and of course it's also a real number. Next we have 2/3. Again, let's go back and take a look at our Venn diagram. Well, 2/3 is in the form of A over B, so it's rational, and all rational numbers are also real. So it belongs to the set of rational numbers and the set of real numbers. Next we have the square root of 8. Let's go ahead and convert this one to a decimal. So second x squared brings up the square root, and then we have 8. So notice how this is a non-terminating, non-repeating decimal. So let's go back and take a look at our Venn diagram one more time. It's a non-repeating, non-terminating decimal, which means it'll belong to this set up here, which is the set of irrational numbers. Remember, in decimal form, it does not terminate and does not repeat. And all irrational numbers are also real. So it's irrational, and it's also real. Now, negative square root 36, we might think that this is also irrational, but remember the square root of 36 is 6, so this simplifies to -6. So we want to use -6 to determine the sets this number belongs to. Well, -6 would be an integer, which means it's also rational and it's also real. In the last example, we have pi. Let's type pi into the calculator and see what it gives us as a decimal. I know we often use 3.14 as an approximation, but pi actually is a non-terminating decimal, and it's also non-repeating because there's no pattern here. So that means pi is irrational and also real. So it's I and R. Now I'm going to go back to 2/3 just for a minute. Let's go ahead and convert this to a decimal to verify that it also satisfies the decimal definition for a rational number. So to convert 2/3 to a decimal, we would have 2 divided by 3. Now the calculator is rounding here. This is non-terminating, but notice how the 6 is repeating. So we have a repeating non-terminating decimal. So if we go back and take a look at the definition of a rational number, again, notice how it says in decimal form, it terminates or repeats. And again, 2/3 was 0.6 repeating, verifying that it is a rational number and also real. Okay, so I hope you found these examples helpful. It may also be helpful to take a look at these sets of numbers as a tree diagram. So you may want to pause the video here and review it in this format as well. Here we have the set of real numbers, rational and irrational, integers, whole numbers, and natural numbers. Okay, I hope you found this helpful.